This is Mrs. O'Neill for AP Chemistry, Chapter 15, Sections 5 and 6, Part 2, the problems. So let's look at these problems. All right, reactants A and B are mixed. Each has a concentration of 0.8 molarity, so that's going to be both concentrations of A and B. They react, they're going to produce C and D. When equilibrium is reached, the concentration of C is measured to be 0.6 molarity. So they're giving us an equilibrium concentration, but only of the product C. And we need to calculate that K value, that equilibrium constant. Okay, first the ice box or the rice box. Why do we call it the rice box? Because a lot of times people put the reaction first. That's first, so that's the R for rice. Okay, if you want to put the plus signs in here, that's fine. And if you want to put the equilibrium arrow in there, that's fine as well. They're not going to be nitpicky about that, but they will be nitpicky about the ice box. A lot of your equilibrium FRQs, that's what they want to see, is this nice little ice box. Okay, so the first thing it says is each of them has a concentration of 0.8. So again, in my readings, 0.8 is going to go in my initial concentrations of A and B. It just says they produce C and D, but they don't give us any initial concentrations of our products. So sometimes they do. If they do, that's where they would go. But if they don't mention any initial concentrations of our products, we're just going to assume 0. Now, what's the next thing? Aha, equilibrium is reached, and it's at 0.6 molarity. So that goes in the equilibrium spot under our product C. Now, this is where it gets a little tricky. How the heck did we get from 0 to 0.6? What's my change in value? Plus 0.6. There's no other way to go from 0 to 0.6 without adding 0.6. Okay, so then that means what's going to be my change value for all those other reactants and products? Well, again, I'm going to go stay here with the products. Remember, products we're always adding, right? Things have to be added. A change has to be added in order for it to reach equilibrium. What happens here as reactants, though? Well, we're going to subtract that change. We're going to subtract it because if that's our change in value, that must mean that our reactants must have changed that 0.6 concentration in order to reach equilibrium. Now you're just going to do the math. 0.8 minus 0.6, 0.8 minus 0.6, 0 plus 6, and 0 plus 6 to get your equilibrium values. Okay, now we can have those equilibrium values. Now we can calculate K. Now we need that K algebraic expression. And in this case, they're all ones. Those coefficients in this example are all ones. And that's why our change as well was all the same. I didn't have to multiply or divide any kind of mole ratio. So did we get what K algebraic expression is? Hopefully you got that. At this point, now you plug and chug those numbers, and you should get an answer of 9. So our equilibrium constant value is 9. Notice no units. Okay, let's move on to 2. Exactly 1 mole. Uh-oh, they're giving us moles instead of molarity. Something to keep in mind. Luckily, they give us 2 liters. Aha, so we're going to use that at the end. When the reaction, that looks like that Haber process reaction, but just in reverse, came to equilibrium. Now we have 0.2 moles of the N2 was found. Again, we're calculating K. So use moles in the icebox first, and at the end, we're going to put in molarity. What do I mean by that? So let's look at that icebox. Can you set that up? Pause the video and come up with an icebox. Hopefully you got the reaction. Hopefully you got rice. And now I'm just adding an extra line for molarity, okay? Because at the end, we're going to have to figure out molarity before we put it into our K algebraic expression. Remember, K is based off of concentration, not moles. All right, now let's read the problem. By the way, I just got rid of molarity, that row, just to give me more space so I can show you more work and information. So exactly 1 mole of NH3 was introduced, so that's our initial. I don't know about you, but I don't see any initial concentrations for our product, so those are 0. Okay, so now our change, it says when the reaction came to equilibrium, 0.2 moles of that N2 was found. So that's where that goes. So my next question is going to be, how the heck did we get from 0 to 0.2? Well, we added 0.2, right? So that's going to be our change in value. Now this is where it's a little tricky. This is a 2 to 1 to 3 ratio. So this 0.2, we're going to subtract, but we also have to multiply it by 2 because of our coefficient. This 0.2, we're going to add over here, but again, we're going to have to multiply by 0.3 because of our coefficient. So did you get those values, right? So 0.2 times the 2 for the NH3 gives us a negative 0.4. Again, we're subtracting here because this is a reactant. The change in value has to decrease. Versus over here, we're adding our change because they're products, we're forming them, right? So we're adding them, but now we have to also remember to multiply by 3 because of our coefficient, okay? So I also want to bring to your attention, if we were given the 0.6 here, and again, we have a 3 to 1 to 2 ratio, we would have had to do some dividing in order to get the other change values, okay? So most of the time they give us the 1 coefficient value and we're multiplying, but every once in a while they'll throw us a curveball and then we're going to have to divide. Okay. So what are our equilibrium values? Again, now do the math. 1 minus 0.4, 0 plus 0.2, 0 plus 0.6, and you should get those values. Now I want to remind you, they gave it to us in moles. So now we're going to need to finish that row on the bottom by calculating molarity, moles per liter. So it's going to be the 0.6 divided by 2, the 0.2 divided by 2, and the 0.6 divided by 2. Now we have our molarity values. Now we can form our algebraic expression for K, plug and chug, and get our numbers. So pause and see if you can do that. Should have gotten, bada bing, bada boom, that equation. Again, products over reactants, concentrations. The exponents are going to be the coefficients from our balanced chemical equation. Now we just put in our numbers, remember to cube and square, and then we have a value of 0.03. No units, remember, no units. Okay, why don't you give it a try? Pause, read, see if you can make a balanced chemical equation if they didn't give it to you. Can you fill in the icebox? Can you figure out the change? Can you now make that change available to all of your reactants and products? Can you figure out your equilibrium values? And then plug and chug. Here's your balanced equation. Again, if you didn't get that to begin with, you might want to pause and redo your numbers. Here is your ice or rice box. And again, I'm putting molarity at the bottom there because they're giving us moles and not molarity. So as a reminder, we're going to need to put that in. My first step was the initial concentration, 100. My next step was 0.14 moles of each of those products. That would have been my next step. Now use the change values there. Now use the change value there, right? So again, we're adding for products, we're subtracting for reactants. And again, notice the coefficients play a big part in our multiplication there. Adjust the moles to molarity. Did we get our K expression or our K algebraic expression to that? Can we put in our numbers? And can we do the math and get 0.038? No units. Okay, we will see you in class, and hopefully this will make sense and doing more example problems.